Hi, this is S.K. Ghosh. On a bright, beautiful Chicago morning, I would like to wish everyone a very pleasant good evening and welcome you to today's offering in our training and capacity building initiative. The today's module is G3. Uh, all morning it will be one module. The title, as you see, is Review of Structural Design, Loads, Construction Practices, and Safety. In, in brief, this is going to be on part 6, very important part 6 and part 7 of the 2020 edition of the Bangladesh National Building Code. And to talk to you on that topic, we have Professor Rakib Ahsan of BWET, who is more competent than anyone else we know to talk about these things. So without any further waste of time, Dr. Rakib, for you, ladies and gentlemen.
Thank you, Dr. Ghosh. Good evening, everybody. Today's topic is review of structural design, loads, construction practices, and safety. I wonder why these part 6 and part 7 all together will be covered in only 2-hour session. Actually, as you can understand, this is impossible to cover everything in detail regarding structural design and construction practices. Actually, in this presentation, I will mainly present the updates that have been included in the new BNBC, new version of the BNBC 2020, mostly the updates, and some topics I will present which were actually in the older version of the BNBC 2 regarding construction practices, because I found that in many cases, many engineers are not really aware of all the provisions that are included in BNBC regarding construction practices. So that's it. Let's start. So this is about part 6, structural design. So what is there in my last night, I presented overview of structural design. There I mentioned that there are 13 chapters in part 6. The chapters are, as you can see, chapter 1 is related to definitions and general requirements. Although the title may sound that the chapter is not that important, basically this chapter is very, very important, and I'll request all of you to go and read this chapter very carefully. There are many important pieces of information in this chapter. Chapter 2, the most widely read chapter, and this chapter is actually covered in our undergraduate curriculum, partly. So most of you are already familiar, so I'll show the updates that have been included in the new version of BNBC. Chapter 3, soils and foundations related to geotechnical engineering. Chapter 4, bamboo structures. This is a new addition. Chapter 5 is related to concrete material. There's some, this is mostly similar to the previous version of the BNBC, but there is one additional topic that has been included in the new version. Chapter 6, strength design of reinforced concrete structure, the ultimate strength design method, USD. This one follows ACI 31808 completely. This follows ACI 31808. Chapter 7 is related to masonry structures. This is also mostly similar to the previous version. Only one new topic has been added. Chapter 8 detailing of reinforced concrete structures. This is very, very important. Actually, these 3 chapters, chapter 2, chapter 6, and chapter 8, these are interrelated chapters. So You cannot design a concrete structure without uh, using these chapters in parallel. Chapter 9 is related to pre-stressed concrete structures. So even in the building structures, recently we use pre-stressed concrete quite often in industrial structures, particularly like post-tension slabs. So this is, and this chapter is arranged in a new manner in this version of BNBC. Chapter 10 is steel structures, is completely written, thoroughly changed from the previous version. It has become very, very big chapter. Chapter 10, there will be a separate session on steel structures later in this program in coming weeks. Chapter 11 is related to timber structure. Again, this is mostly similar to the previous version. There are some new additions. Chapter 12 is ferrocement structures. This is probably completely similar to the new version. There are no changes in this chapter. Chapter 13 is a new chapter, steel, concrete, composite structural members. I explained to you yesterday, that is, this is related to composite structures. That is, when we use in the same structural member both steel, structural steel, and reinforced concrete. So let's see what is there in chapter 1. There are many things, but I'll just emphasize on few topics. First, what is the definition of structure according to the building code? Structure, an assemblage of framing members and components arranged to support both gravity and lateral forces. Basically, that part of a building, say, or non-building structures that carries the load. That is the structure. Building structures enclose a space and are used for various occupancies. When we have different types of occupancies, people may reside, people may use for different purposes. That makes it a building, and the structure of a building is a building structure. Non-building structure other than buildings such as water tanks, bridges, communication towers, chimneys, etc. are non-building structures. Now, are non-building structures covered in the building code? Yes and no. For example, even for the design of non-building structures, we use the building code to determine load. For example, the seismic load. You use the zonation map even to design bridges or other non-building structures. And there are some tables related to wind load, related to non-building structures. So from that perspective, this is partly covered, but the details of design of non-building structures are not covered in the building code. Now, this is quite familiar to you. This is the occupancy. As I said yesterday, that we categorize buildings in different ways. For structure, for the purpose of structural design, we categorize building in one way. For the purpose of seismic design, we categorize building in a different way. For the architectural purpose, we categorize in another way. For administrative purpose, we categorize. So there are different categorization of building. For structural design purpose, the most important categorization is this, although the name is very similar to the architectural categories. That is also called building categories on the basis of occupancy. And in structural design also, we call it occupancy category. Basically, this is risk category. How, if a building collapses, what might be the risk? What would be the consequence of the collapse? It is related to that, this structural occupancy category. Now, you know already, because this is similar to the old building code. The first one is low hazard to human life. That is, if a building collapses, if there is very little probability that human lives will be in danger, then that is low hazard. For example, silo for grain to store grains, for example, rice or sugar, uh, a silo storage. So if it collapses, there will be economic loss, but there's very little chance that human lives will be in danger. So that is a low hazard billing. I'll come to the second category later. Let's go to the third category. There is substantial hazard to human life. The billings for which if a building collapses, if there is chance of casualty of human lives, like an assembly building, like a stadium, like a where many people gather. If the building collapses, then there is chance of many casualties. That kind of building will be like in the third category, substantial hazard to human life. Fourth category are essential facilities. That is, in the event of a disaster, like if an earthquake happens or if a flood disaster happens, the buildings that we need to be operational uh, for the purpose of emergency response. For example, after an earthquake, we would need fire service, fire stations to be operational. We need hospitals to be operational. We need police stations to be operational. We need evacuation centers to be operational. Those buildings, which will be needed just after a disaster, they are called essential facilities. So they come in the fourth category. Then what about the second category? All other buildings like residential buildings, office buildings, they are called standard occupancy. They come in the second category. So I think most of you know about these categories. So that is unchanged. Building basic structural systems. These are also mentioned in the previous version of the code too, but I found that many engineers are only familiar with the moment resisting frame system. They're not familiar with other systems. Now, actually, there are different structural systems. The first one is very simple, bearing wall system. That is like our old type brick buildings. That is the brick walls that carry both gravity load and that has a limited capacity to take lateral loads. Bearing wall system, but if it is properly designed, it is supposed to carry the lateral loads too. So bearing wall system, I think you are familiar with that. Building frame system. Building frame system is interesting. Although the term frame is there, you may think that this is a beam column system. Yes, frame is there, but the typical beam column systems that we are familiar with are actually moment resisting frame systems. So what is a building frame system? The frames, that is beam column frames, they carry the gravity load only. The lateral load is completely carried by shear walls or bracings. So the shear walls or bracings are designed to carry the lateral load, and the frames, beam column frames, are designed to carry the gravity load. So that kind of system is called building frame system. Now, what is a moment resisting frame system then? In moment, we all know that moment resisting frame system, the frame beam column frames, they carry both the vertical gravity load and the lateral load. So, okay, I have some animations. And we all know that in the building code, there are mentions of 3 types of moment resisting frames: ordinary moment resisting moment frames, intermediate moment frames, and special moment frames. I think most of you know about these classifications. These are related to detailing, that is how ductile the frame is, what amount of inelastic deformation a frame can go through. So ordinary moment frames are not very ductile. They collapse after some deformation. Intermediate moment frames are somewhat more ductile than ordinary moment frames, and spatial moment frames are very ductile. So they can absorb a lot of energy during inelastic deformation. So we'll see some more details. Actually, Dr. Ghosh will give lectures precisely on these topics in the later sessions in the coming weeks. Dual system, I think many of you know about these. Dual system has both frame, beam column frames, and shear walls or bracings. The difference with bearing frame system and dual system is that in dual system, the beam column frame, the beam column frames in a building, they do also carry a portion of the lateral load, at least 25% of the lateral seismic load. If that is the case, then we'll call that a dual system. There may be other special structural systems like tubular structures, tube in tube, and there are many other different types of structural systems. Those are termed as spatial structural systems. So all of us should have basic knowledge about these structural systems. Now, there is another very important aspect of structures, that is a building structure can be regular or irregular. Many things depend on this classification. So if we know what are the irregularities are, then if a structure doesn't have these irregularities, then they automatically become a regular structure. Now, what are the irregularities? The irregularities are classified in two classes. One is called vertical irregularity, that is the irregularities that we can see from elevations of a building or sections, elevational sections of a building. Those irregularities are called vertical irregularities. And the irregularities that we can see from plan view, from top view or plan view of floors. If we find irregularity in floor plans, then those irregularities are called plan irregularity or horizontal irregularity. Now, let's see what are the vertical irregularities. Vertical irregularities, there may be five types of vertical irregularities. One is soft story. We quite often hear this term, soft story. Now, what is a soft story? This is related to stiffness. If the stiffness of a story is much less, there are specific numbers like 70% or 80%. I would encourage you to read the code to know the exact number. If a floor stiffness is much less than the floor stiffness of the adjacent floor, then the floor is called soft story. Now, there are two types of actually soft story and extreme soft story. And not only the adjacent floor, adjacent two floors maybe. If a story, we compare the story stiffness with the adjacent floor and adjacent two stories. So whatever, please read the code to know the exact definition. What I want to show here is that how can a story be less stiff than an adjacent story? One quite typical example is that the parking floor, the ground floor of an apartment building, where we don't have any brick walls, whereas the other upper stories, they do have brick walls. So brick walls are actually very stiff. They are quite weak in terms of strength, but they are quite stiff in terms of stiffness. So they may be broken quite easily, but it is difficult to deform them with unit amount of force. So that is the definition of stiffness. So if a story is devoid of any brick walls, whereas the adjacent stories have brick walls, then the story without the brick walls becomes soft story. That is one example. Another example may be that if you stop a shear wall at a certain height suddenly, then the upper story may be a soft story compared to the lower story. So this is related to stiffness. And why is it so important? Because in many earthquakes, it was found that these soft stories collapse very easily during earthquake. So there are a lot of literature regarding this. So this is one type of irregularity. Second irregularity is mass irregularity. If a certain story is quite heavy compared to other stories, for example, if a story has a heavy equipment, or if a story used as a library, many books are stored there, or in government factory buildings, it is very common that in one story they store fabrics. The fabric rolls are very heavy and they store them, a lot of them in one story. Recently they store usually in the ground floor, but previously we found that in many cases they stored in upper floors, even in the top floor in many cases. So that floor, which have heavy load compared to other floors, that story becomes that causes mass irregularity. Vertical geometric irregularity, for example, if some bays are discontinued and other bays are continued in the upper floors, then that may cause a vertical geometric irregularity. In plane discontinuity, in one plane of a frame, if say column is shifted, shifted, then that causes in-plane discontinuity. We can see this discontinuity in the plane of the frame. That's why this is called in-plane discontinuity. Sometimes we call it floating column. So that's another type of discontinuity. Weak story, this is very similar to soft story. The only difference is that we compare not the story stiffness, rather we compare the story strength compared to other stories. Now, for example, in the case of soft story, brick walls, they are not quite strong. They cannot take a lot of lateral load. They break easily, but they are very stiff. So the absence of brick wall in one story makes it soft story, but it doesn't make it a weak story. But if we discontinue shear wall, or the lateral load carrying member is section of a lateral load carrying member is reduced, that may cause a story to be weak story, because that reduces the strength of the story. So these are examples of vertical irregularity. So we have to be very careful about these irregularities. The most common type of irregularity that we find in Bangladesh is the soft story. So we have to be very careful about that. Regarding plan or horizontal irregularity, one example is torsional irregularity. If we place shear walls in an eccentric way, then that causes torsional irregularity. For example, in the picture, you can see the shear core, which we usually call shear core, that is placed at one corner of the building. So what will happen during an earthquake, that this stiff core will be pinned at this place, and the columns at the floor will be twisted, will be rotated, making this stiff core as the center of rotation. So there will be twisting on the columns of the building. So there will be torsional uh, uh, fractures in the columns. So this is very common in earthquakes when this, due to torsional irregularity, buildings collapse. So this is important. This is very important for the architects too. The architects all should be aware of this thing. Now, they may ask that, okay, then can't we have any shear core placed eccentrically? Should we always place the shear core or shear walls in a symmetric way? The answer is no, but if we allow torsional irregularity, in that case, we have to design accordingly. So we'll see later what are the provisions that we have to follow if a building has certain kinds of irregularities. Reentrant corners like these L-shaped buildings or T-shaped buildings or U-shaped buildings, where they're like, for example, if this building, you can see in the picture, I'll try to use my laser pointer here. So if the ground vibration is in this way, you can see this part is quite stiff because this is the longer side. If it vibrates in this way, this part is stiff, but this part is quite flexible. And so this part will vibrate quite heavily compared to this part. And in this corner, there may be cracks because there will be stress concentration at these corners. So this type of corners are called reentrant corners. So the buildings, it's always better to separate them, providing a gap. We call it seismic gap. So if we do not provide any seismic gap, if they are joined together and make this kind of corners, they're called reentrant corners, and that's a plan irregularity. Diaphragm irregularity, if we have punches like these in a diaphragm, like that is the floor slab, then if the size of the punch is quite substantial, it is written in the code what percentage of the floor area we can allow for the punches. If the opening is quite large, in that case, it may become diaphragm discontinuity. Out of plane offset, you can see these offsets. So for example, this vertical member, that is lateral load carrying member, but vertical. As you can see, this is a shear wall. So this has been discontinued here and placed on a different bay. So you can see this discontinuity in floor plans. That's why this is a plan irregularity. So when the shifting is in a different elevation, then this is called out of plane offset. And in the previous case, in plane offset, you can see the shift in the same plane of elevation. So that is the difference. So this is out of plane offset. And non-parallel system, if the grids of frames are not parallel, then they're called non-parallel system. So these are the irregularities that we have to be very careful about. Now, why do you need them? We'll see later. Now, another important topic that is included in chapter 1 is related to drift, allowable drift serviceability. So the story drift that will be that may be allowed, it depends not for the seismic case, for other types of loads. For all other types of load, we can allow this much of inter-story drift, simply story drift. That is the drift between two floors divided by the story height. So that is the drift. This much drift we can allow. It depends, you can see, it depends on the period of the structure. I hope you understand what we mean by a period of the structure. That I hope you all know about this, but still I want to just mention that by the period of a structure, we mean that if every structure has its own period or periods, every structure has a fundamental period. Fundamental period is that if a structure is, say, pulled in one direction, and if we remove the pull, then it vibrates. Yes, it vibrates, right? Then the time it takes to come back to its original position or to make one cycle is called period of that structure. Very simply, if I say very simply, then that is the period of the structure. That if I pull a structure in one direction and remove the force and make it free, if it vibrates freely without any force, and it goes to the other direction because of vibration and come backs, and the time that is required to make one cycle, that is called period of the structure. Now you can argue that, well, a structure, if I pull a structure with different amounts of force, the time that will be required to come back to original position or to make one cycle will be maybe different. That is not the case. It depends on the mass and stiffness of the structure, and the same structure, whatever the amount of force you pull it, will take the same amount of time to make one cycle. So if you want to understand more about this, you have to study structural dynamics. So just know that every structure has its own period, and we can calculate that period. And depending on the period of the structure, it mostly depends on the height of the structure. So if it is a tall structure, then the period is long. If it is a short structure, then period is usually short. So depending on the period, in other words, depending on the height of the building, these drift criteria is set. Now, there is another criterion that has been introduced in this version of the code that is only for wind load. Now, only wind load. For only wind load, the total amount of sway at the top of the building, at the top level, not interstory drift. The total amount of sway only for wind load must be less than this stringent number, 1/500. So this is something new that has been introduced in this building code. Now, seismic drift, although this is not part of chapter 1, this is actually part of chapter 2, but I have included this information in the same slide so that you know that there is a separate clause for drift limit for earthquake loading. The seismic drift that has been related to occupancy category, basically for different occupancy categories, that is the risk categories, like for low hazard building and standard occupancies. And this is the story height at a particular level. For different occupancy categories, this is occupancy category 3 is hazardous buildings, and occupancy category 4 is essential service buildings. So for different categories, the service limit. For earthquake loading is different. But in addition to these, there are a lot of things written in the same clause, particularly for seismic design category D, that we'll know in very short time what is seismic category D. But for different seismic design categories, these vary. We may need to be stricter. We have to divide these numbers with some other number, more than one probably. In some cases, and it also depends on whether we are conducting a linear analysis or a non-linear analysis. So it depends on many other things. Please read those clauses carefully to actually be able to check this criteria. Now, this is something that is quite often overlooked. That is in this chapter, chapter 1. It is related to design document. That is, when we submit a drawing for approval, what are the documents that we are supposed to submit? Now, in case of Rajuk and other development authorities, they follow the building construction rules, PC rules, like Imarat Nirman Vidhimala. So in the Vidhimala, there are prescriptions that what have to be submitted. But according to the code, these documents have to be submitted. So those in the PIU and Raju, I plead to you, please show this to the Imarat Nirman Vidhimala committee. So the rules in the Imarat Nirman Vidhimala do not conflict with the building code. So the documents that are supposed to be submitted during submission should be similar, both in the building code and Imarat Nirman Vidhimala. So what are the documents that are supposed to be submitted? A design report, material specifications, structural drawings, mention of BNBC. For example, now it has to be BNBC 2020, name of other reference standards, a drawing of the complete mathematical model. What do you understand by this? Let me give an example. For example, in order to understand the effect of the soft story building, we need to model the brick infill walls. So how can we model? We can model it in many different ways. For example, we can model it as struts. If we do that, then in the mathematical model, the drawing of the mathematical model, the walls, brick walls, should be shown as struts instead of walls. So that is the mathematical model. Methods of structural analysis and results of the analysis. There are different methods of structural analysis. We'll see, for example, to consider earthquake loading, what are the different methods of analysis we'll see. So which method of analysis is followed should be mentioned, and results of the analysis. Methods of structural design, including types and strength of the materials of construction, reference of the soil report, statement supporting the validity of the above design documents with date and signature of the engineer responsible for the structural design. So it must be an enlisted engineer who can sign. In addition to that, in the structural drawings, what should be there? It is mentioned sheet by sheet, in what should be there in the first sheet, what should be there in the second sheet. That is interesting. So we should all follow these guidelines. In the first sheet, identification of the project, reference to the design report, date of completion of design, identification and signature with date of the engineer responsible for the structural design. The second sheet shall contain material specifications, specified compressive strength of concrete at stated ages. For example, we need the 7-day strength of concrete so that we can decide if we can remove the props or not, things like that. Or in case of pre-stressed concrete, that is very important, when we can jack the concrete. So we need initial strength, things like that. Specified strength of or grade of reinforcement, if it is whether it is 400 MPa or 560 grade or 72.5 grade or 40 grade reinforcement. Uh, we should actually, in my opinion, we should mention the BDS standard nomenclature like B400DWR, that nomenclature, because that is the standard of Bangladesh, BSTI standard. Specified strength of pre-stressing tendons or wears, if there is any pre-stressing. Specified strength of or grade of steel. This steel is actually structural steel. If you use any joist or channel sections, so what is the grade of that steel? Specified strengths of bolts, welds, etc. Specified strength of masonry, timber, bamboo, ferrocement. Concrete compressive strength at time of post-tensioning. Stressing sequence for post-tensioning tendons. General notes indicating clear cover, development lengths of reinforcement, or any other design parameter. Identification and signature with date of the engineer responsible for the structural design. And then drawing sheets shall include structural details. Drawings shall be prepared to a scale large enough to show the information clearly. Each drawing sheet shall also contain the signature with date of the engineer. So this is quite detailed, all the information. So we should follow these guidelines. So that was all about chapter 1. I took a lot of time covering chapter 1, but I think this chapter is very important, but this is not read widely. So, but this is very important. There are many more important pieces of information in that chapter. Please read that chapter carefully. Chapter 2, loads on buildings and structures. This is one thing that we are very familiar with. So what are the loads? Dead loads, live loads, wind loads, earthquake loads, and miscellaneous loads. Miscellaneous loads like rain loads. Do you really calculate rain loads? Please check what the code says. Loads due to flood and surge. Do you consider that? If you're designing a structure in the coastal areas, you should. And please read the code, how to calculate these loads. Temperature effects, soil and hydrostatic pressure, loads due to explosions, vertical forces on air raid shelters, loads on helicopter landing areas, erection and construction loads. So these are the most frequently used ones: dead loads, live loads, wind loads, and earthquake loads. Let's see them. Live loads. We know that in the previous version of the building code, there was a table mentioning loads for each type of occupancy. Occupancy, by occupancy type, I refer to the architectural classification of occupancy. For example, residential building, institutional building, or industrial building. For those occupancy types, the recommended live loads were mentioned in the previous version of the code. But this time, a different format has been used, and this is actually from AC7, basically AC705. So similar to AC7, the classification actually doesn't always follow that occupancy classification. It is a bit different, but please follow this classification. Here, only 2 rows have been added. All other things are just similar to SC7, only 2 rows. One is this: garments manufacturing floor except stacking or storage area. So for garment factory buildings, there have been a lot of disputes and controversies regarding these things, because when this code was being drafted at that time, just actually in 2013, Rana Plaza, the tragic event of Rana Plaza happened. Just after that, all the assessments and retrofitting works that started. So these were very important. So these two new roles have been added in the this table. One is for common floors, like without the storage area. The recommended live load is 4 kilopascal, 4 kilonewton per meter square, which is equivalent to 80 PSF. And for storage areas, this is 6 kilopascal, kilonewton per meter square, which is equivalent to 120 PSF. But do you think this is enough? 160, 120 PSF? I think many of you who have experience in assessing garment factory buildings will disagree. They would say that it is very common that in the garment factory building, in the storage areas, the live load exceeds this value. Yes, that has been considered even in this code too. It is mentioned that if the storage height is 3.5 meters or less, only that case you have to take 6 kilonewton per meter square. If the storage height is more than that, you have to extrapolate this. Like if this is like 4 meter height or 4.5 meter, then you have to increase it proportionally, this value. So that's it. Reduction of live loads, I think you know about this. I think this was there in the previous code too, but still it depends on the tributary area. If I think this is automatically taken care by many software, but still if the tributary area of live load is above certain value, then you can reduce the live load. So these are the clauses. But if the recommended live load is more than 4.8 kilonewton per meter square, you are not allowed to reduce live load. Things like that. Wind load. Okay. Wind load, the procedure has been changed completely. In the previous version, it was different, a bit simple, much simpler than the present version. The present version of BNBC follows exactly AC705. So all the steps are absolutely similar to AC705. That is an advantage for design engineers, that you can blindly use the available software. You have to just select for load calculation AC705 code in the drop down menu of your software. That will take care of everything, but you have to be aware of the steps and many details. So these are the steps: the basic wind speed and wind directionality factor. You have to first determine these, then importance factor, which depends on occupancy, exposure category. It was there in the previous code, but it was much simpler. Now, first you have to identify surface roughness in different directions, and from surface roughness, you have to understand the exposure category. So it has become a little bit different. A topography factor, if it is on a hilltop or different types of topographies are mentioned in the code, in a table actually. So based on the topography pattern, you have to consider a topography factor. Gust effect, it was there in the previous code. Now there are many diagrams from which figures, it is called figures in the code, from which you have to calculate then determine these factors. And enclosure classification is there, that is, it is completely enclosed or partially enclosed or open type. Based on that, your calculation will be different. Internal pressure coefficient, it was there in the previous method too, in the earlier version of the code. External pressure coefficients were also there, so these should be familiar to you. And there are a lot of tables for these from which you can determine these quantities. Velocity, pressure, the formula is different. Now this form to calculate pressure, all these factors will be needed. And once you can calculate the pressure, then you from the area you can calculate the force. So basically many different factors that you have to calculate this time. The most important one is the basic wind speed. So the basic wind speed map, if you compare with the earlier version of the code, you'll see those two maps look exactly the same. The values are different. Why is it so? Actually, no new calculations were done this time because the code in the previous version was quite conservative. Even with the latest data, the actual speed that we can derive to calculate wind load is not that conservative. So we became conservative and we followed the previous version of the code. So the contours and everything is similar. Well, then why are the values different? First of all, the unit is different. In the previous version, it was kilometers per hour, and in this version, it is meters per second. But if you directly convert the kilometers per hour from kilometers per hour to meters per second, you will not get the same values because there is another conversion. In the previous version of the code, that was based on fastest mile wind speed, a different method of measuring wind speed. And this time, this is 3-second gust wind speed. So the basic method of measurement is different. So there is a conversion for that. AC 705 follows 3-second gust wind speed, and our previous version of the code followed fastest mile wind speed. So we needed a conversion for that. That's why the values are different, but the contours are the same. So this is it. Exposure category actually depends on surface roughness. These are basically surface roughness definition: urban or suburban, open terrain, flat, unobstructed areas. Based on that surface roughness and with some other information like to what extent the open terrain is or flat unobstructed areas is, the exposure category is determined. And this is important. All the calculations become different if a structure is too flexible. That if a structure is very tall, then we call it flexible or dynamically sensitive structure. Previously, it was called slender structure. So it depends on the period, basically height of the building. If the period of the structure is more than 1 second, then that is flexible structure. So the calculations become different later. And we also have to consider if the structure is closed from all sides or partially open, or partially enclosed or open. There are definitions. Please read the code carefully. Based on these, the calculations become different. So these are the new things. So the procedure is completely different from the previous version. So you, although the application with software will be much easy, but you should read the code to have an in-depth understanding so that you put correct parameters in the correct boxes of your software. Now, let's talk about earthquake load. Again, it is different this time. The method is completely different from the previous version of the code. But unlike the wind load, this is not exactly similar to AC 705. There are some differences, but at the same time, there are ways where we can just simply use the software the similar way. Just we can choose AC7. So those shortcuts are given also in the code. Let's see. Uh, to before going to the earthquake load, the very important classification, this site is different this time. Previously, in the previous version of the code, there were 4 site classes, S1, S2, S3, and S4. This time, it is different. This time, there are 7 classes, SA, SB, SC, SD, SE, and S1, S2. SA is rock, SB, very dense sand or very stiff clay, SC, medium, SD, loose, SE is SC or SD underlined by stiffer material. That is, if the difference of soil strength is abrupt. In that case, S1 is if the is plastic soil, if the plasticity index is very high. S2 is other problematic soils, liquefiable soil, very sensitive soil, etc. But in the previous version of the code, the soil classification was based mainly on SPT values, standard penetration test values. But this time you'll see that in many cases we have to depend on average shear velocity, or we can use either n values or average shear velocities. So for example, to classify S1, there is no mention of n value. There is only mention of shear velocity, like in case of SA2. So I think most of you know about how the shear wave velocity. For example, to have SPT values, we have to do SPT, standard penetration test. But to have CPT values, we can use like bone penetration test or PS logging test. There are other different methods of testing that we can employ to determine shear velocity. Or from the laboratory tests, we can determine undrained shear strength and classify the soil. So that's it. Average. What do you mean by average? 30-meter average. This average means actually 30 meter, 100 feet. This is the average of 30 meter. Anyway, now that was site classification. The most important factor that you know we need to calculate earthquake load is the zonation map, zone coefficient. Zone coefficient. Zone coefficient, in the previous version of the code, Bangladesh was classified in 3 different zones, zone 1, 2, 3. Zone 1 was the southwest part of the country, comprising from here like Kushtia, Jessore, Khulna, Satkira, Bagerhat, Barisal, Faridpur, Noakhali, this part. And zone 2 was like Dinajpur, some part of Rangpur, Rajshahi, Bogura, Dhaka, Kumilla, Chittagong, and Chittagong Hill Tracts. And zone 3 was the northeastern part, so Kurigram, Sherpur, Rangpur, Mymensingh, and Greater Sylhet. So this part was zone 3, and the zone coefficients were different. This time it is changed. This time Bangladesh is divided in 4 seismic zones. Zone 1, Zone 2, Zone 3, and Zone 4. Zone 1 is this part, similar to Zone 1 of the previous version, but a small part of Zone 1 is, this time it is Zone 2, the southern Satkira, Khulna, and Bagerhat part. This is zone 2. So zone 2 in two separate areas, disjoint areas. So why is it so? Because recently geologists are saying that there is an epicenter near Calcutta. So that increases the seismicity of this part. And the previous version of zone 2 is kind of, zone 2 and 3 is kind of divided into the new version of zone 2 and new 3. There is this zone 4. Previous version of zone 3 has become zone 4. So why is it so? As you can understand, the seismicity of Dhaka and Chittagong is actually different. Chittagong is more seismically active region than Dhaka. So it is very natural that they belong to two different zones. So this time, this part, Dinajpur, from Dinajpur to Nauga, Natur, Pabna, Rajshahi, Dhaka, and Kumilla, and some part of Noakhali, this is zone 2, and here also southern part of Satkhira, Khulna and Bagherhat. Zone 3 is this part, which is Rangpur, Bogura, Jamalpur, Tangail, Gazipur, and this Greater Chirang and Chirang Hill tracts. And zone 3 is Kurigram, Mymensingh and Greater Sylhet. Zone 4, this is zone 4. Now you can say, is it arbitrarily the zonation? Is it arbitrary? No. There have been background studies. This has been proposed basically by Professor Tahmid Malik Al-Hussaini. He worked on this. He did probabilistic seismic hazard assessment, PSHA, and then this was derived. Now, the second question is, what about the zone coefficients? In the earlier version, the zone coefficients were much smaller. This time, this is much higher. Like in case of these, this is 0.36, 36% of gravitational acceleration. It seems quite high. Why is it so? Does it mean the earthquake load that we used to calculate with the previous version will be much higher? Now, the first answer is no. It will not be proportionally higher. This is because the subsequent calculations are different. The formula that we use with this zonation map are different from the formula that we are going to use with this zonation map. So there is difference. Secondly, the probability of earthquake that was considered in the previous version was different from this version. Here, as usual with other building codes like ASC 7, other standards or codes like ASC 7, the maximum considered earthquake, MCE, has been considered for this zonation map. The definition of MCE is, probably I have another slide, but still I want to mention here, the definition of MCE is 2% of probability of accidents in 50 years. So in 50 years, if an earthquake has a probability of accidents of only 2%, that is called maximum considered earthquake. In other words, the return period is 2,475 years, like almost like 2,500 years. So if the probability of an earthquake, the return period is 2,500 years, so that large an earthquake is called maximum considered earthquake. And if that kind of an earthquake happens, occurs in a nearby place, the ground vibration that may occur in different places of Bangladesh, this is a kind of worst scenario for that. So this is it. But the probability of earthquake that was considered in the previous version was different, was for much lower earthquake. Now you can ask that why are we considering this such a large magnitude of earthquake this time. Actually, we are not going to design for MC. We'll reduce this with using formula. We'll reduce, and ultimately the earthquake we design a structure for is called design basis earthquake, which is 10% probability of accidents in 50 years, or the return period is 475 years. That is the standard. Now, it is usual that the zonation map is produced for MCE, maximum considered earthquake, but the design is done for DB, design basis earthquake, and the formula takes care of that. Let's see. So based on that, design spectrum, a set of design spectra have been proposed in the building code. This is actually not very different from ASC 7. What does it have? This is the value of acceleration considering the properties of soil, site class, and the building parameter, like the period of the building. So if we know the period of our building, and if we know the site class, then we can calculate the acceleration. Okay. So using this and this multiplied by the PGA rock, that is, another thing. These accelerations are actually for if the soil is rock, then it is supposed that this amount of acceleration will happen. And the topsoil, the properties of topsoil are taken care here. So we'll have to multiply this value with the Z value, and then we'll get the acceleration. No, now this is very important, seismic design category. This is a new concept. Previously, in the previous version of the code, we were free to choose if we could design a structure as an ordinary moment frame or an intermediate moment frame or spatial moment frame. What we used to do, if we considered a structure to be a special moment frame, then we would reduce the load using a greater R value. That's all. But there was no restriction if we could use ordinary moment frame or special, intermediate or special. This time there were some restriction based on zone, but this time the restrictions are based on zone and site class and occupancy category. For occupancy categories 1, 2, and 3, this is the table. But for occupancy category 4, there is another table, an extension of this table, but I've omitted that for to make it simple. So, for example, let's talk about Dhaka. So Dhaka belongs to zone 2. Now, there are 3 seismic design categories, B, C, D. Why does it start from B? Because in the SC there is another category A, which is not applicable for our case. So we have maintained consistency in the definition of the categories B, C, D, but we omitted A because that is not applicable in our case. So that's why it starts from B. Now, 3 design categories. What do they actually mean? I'll come to that point later. But first, let's see how to choose which category you have to design a structure. For example, in case of Dhaka, which is in zone 2, we can design a structure. No, sorry, Dhaka is in zone 3. Really? Zone 2? No, zone 2. And Chidang in zone 3. Dhaka, zone 2. We can design a structure as seismic design category C if the soil condition is good. if the soil is rock or very stiff or medium stiff. If the soil condition is loose or soft, then we have to design the structure as design category D. Or if there is abrupt difference in soil strength in the top layer, AC, or if the soil is plastic soil, or the soil is liquefiable or problematic soil, then we have to design the structure as design category D. So if the soil condition is not good, we have to design a structure as SDCD. But if the soil condition is good, then we can design a structure as seismic design category C. In case of Chittagong, things are quite different. If we build a building on top of rock, only in that case we can design a structure as seismic design category C. Others, the structure has to be designed as D category. In case of Silet, Mymensingh, Kurigram, Zone 4, all structures must be of design category D. Okay? Now, there are definitions of seismic design categories B, C, D, simply saying, in a simple way, if I say that ordinary moment frame actually correspond to SDCB, IMF, intermediate moment frame, correspond to somewhat zone SDCC, and special moment frames correspond to D. Then you understand that in Silet, you can never design a structure considering IMF or OMF. The structure must be SMF. In Chittagong also, if the structure is not on rock, it must be SMF. In Dhaka, you can design a structure as IMF if the soil condition is good. Otherwise, it has to be SMF, special moment frames. So that's a simple way of saying this, but you have to read the code to understand it properly, how to make a structure SDC B, C, D. Now, there are height limits too. For example, in case of special steel moment frames, intermediate steel moment frames, there are limits. Let's see seismic design category D. Ordinary moment frame is not permitted. Intermediate moment frame, for concrete, is not permitted. So you understand, that's why I said actually design category D correspond to special moment frame. So there is no height limit for design category D if we construct a special moment concrete moment frame. In case of steel, ordinary is not permitted. Intermediate, you can use intermediate steel moment frames, but there is a height limit of 35 meters. Okay, so, and special for moment frames, there is no limit. So this is like this. Seismic design category C, you cannot make an OMF that is not permitted in SDCC, for SDCC, but there is no limit for IMF or SMF. So that's why I said it corresponds to IMF. But there is no restriction on building SMF for seismic design category C. And B is, there is no limit for ordinary moment frames. So this table is a big table for other building configurations or building categories. What is it? Building structure systems. There are mentions of height limits for different seismic design categories. Oh, it is there. It is there. So at the same time, the R values are mentioned, and for calculation of deformation, CD values are there, and the height limits are mentioned here. Okay, so this is the Bigger table. So one thing now you can appreciate is that design categories are related to building systems, structural systems, and their height limits, but there are many more that we'll see. Now, another important thing is that method of analysis. For earthquake loading, what method of analysis we can adopt? We are used to using applying equivalent static load method, but this time, and in the previous code also, there were restrictions, but this time the restrictions are much more stricter. For regular buildings in zones 2, 3, and 4, if the height of the building is more than 40 meters, like 13-story and above, you have to adopt a dynamic analysis method. You can no more use equivalent static load method. In zone 1, the limit is 90 meters, like 30-story or above. So you see in Dhaka, Chittagong, Sylhet, for a regular building, if there are no irregularities, only in that case, if the height of the building is less than 40 meters, then you can use equivalent static method. Otherwise, you have to use dynamic analysis method. But you see, for irregular buildings, this is so much strict. In zones 2, 3, and 4, if the height is more than only 12 meters, like 4-story, can you imagine? You're going to design an apartment building. Usually in Dhaka, the apartment buildings are all 6-storied, 7-storied, and above. And the architect has designed a parking floor in the ground story. Then that makes it a soft story. So there is a vertical irregularity, and the building is 6-storied or 7-storied. This is irregular building more than 12 meters of height. So you have to use dynamic analysis. You can no more just resort to equivalent static load method. So this is something very, very important. I emphasize that the design engineers be prepared, be ready to use dynamic analysis. You may think that it shouldn't be that difficult. The software will take care of that, but that is not the case. You have to understand the dynamics, structural dynamics, if you want to really be efficient in design, if you really understand what's happening. So I would suggest every one of you should study structural dynamics and be confident in using dynamic analysis. The other considerations that are important for loading, this is seismic weight. In the previous version of the code, dead load, permanent dead load was the seismic weight. In case of storage or warehouses, we would consider some portion of live load and add that with dead load as seismic weight. But this time we have to consider some part of live load as seismic weight. Like if the recommended live load is less than 3 kilonewton per meter square, like 60 psf, then dead load and 25% of the live load will be considered as seismic dead load or seismic weight. If the recommended live load is more than 3 kilonewton per meter square, then 50% of the live load should be added with the dead load. Now, the other points, like if the building has horizontal torsional irregularity, not irregularity, torsional moments, like we have to calculate for lateral load. If there is torsion, we can calculate that. We have to calculate the average deformation of a story and lateral deformation of a story and maximum lateral deformation of story, and from those values we can calculate if there is torsional moment or not, that we need to consider. And then we have to take that into consideration in our calculations, like we need to magnify the moments. So these things are very important that we all should be conversant with. Then pedal effects, that there is a factor or parameter called theta that we have to calculate to understand if we need to calculate pedal effects or not. This is very important. Simultaneous loading in principal directions. In the previous version of the code, we used to calculate earthquake load only in X direction and only in Y direction. And then we had to analyze the two cases separately. But this time, when we will consider load in the X direction, at the same time, we have to consider 33% of the load of the Y direction simultaneously in most of the cases. In some cases, then we don't have to, but the way we design our buildings in Bangladesh, in most of the cases, single vertical member takes loads from or resists loads in both the directions. That's why these simultaneous applications of loading will be required. So this is something new that you have to understand. This time there is consideration of vertical earthquake loading. So in the previous version of the code, we used to calculate earthquake load E only for horizontal loading. Now this time there are two components of E. One is EH horizontal and EV vertical. So in the definition of earthquake load is not only horizontal load, there will be a vertical component too. And that will be important for buildings having long cantilevers. Seismically isolated buildings. So I don't know if you are familiar with this term, isolated building. Maybe you have heard the term base isolations. Base isolation buildings, those have kind of bearing at the bottom of the columns on top of footing, and the bearings are such that isolates the building from ground vibration. Because of ground vibration, the bearing takes the energy and the superstructure, the building vibrates very little. That kind of system is called for base isolation. For if a building has that kind of system, so the spatial requirements for those buildings are mentioned in this clause, in this section of chapter 2 of part 6. And for buildings with soft story, there is a special shortcut that if you determine that there is soft story, but you don't want to make detailed analysis, dynamic analysis, there is a shortcut. Actually, this is taken from Indian Building Code, that you can, only for soft story, you can use equivalent static loading, but you have to magnify the moments in the ground floor, in the soft story, usually the ground floor. You have to magnify the moment. Okay, so in that way, there is a shortcut only for soft story that you can still you can use equivalent static load method. So these are special considerations. If I go into the, I think Dr. Ghosh will go into the details of these things in later sessions. Now, seismic detailing. This is chapter 8 actually of part 6. This is very important. As I said, loading chapter 2, concrete design, reinforced concrete design, chapter 6, and chapter 8, detailing. These are interrelated chapters. So In chapter 8, there are provisions for detailing, ordinary detailing, not seismic detailing. Ordinary detailing, there are provisions from 8.1 to 8.2, 8.1 and 8.2, that is related to hooks and other things. That is applicable for all types of loading. For earthquake loading, seismic cases, these section from 8.3.3 to 8.3.10 are related to seismic detailing. Now here you see the detailing, that the way how we are going to design the ties or spirals, confinements of of a column, or how we are going to design the stirrups of a beam, what should be the lap length, or what should be the anchorage, things like that. So the detailings and the hooks, the details of the hooks, these details that are mentioned in these sections, but they are related to seismic design category. So seismic design category is very important. Based on seismic design category, you determine if certain height of the building is allowed or not in specific zones. You determine the value of R, you determine the value of CD. So the loads are calculated based on seismic design category, and then design, and after the design, the detailing depends entirely on seismic design category. So for seismic design category D, we have to follow these sections from 8.3.3 to 8.3.8, 6 sections, and these are quite extensive. A lot of provisions are there in these sections. So all the requirements in these sections have to be complied if we want to build a seismic design category D building. For seismic design category C building, we have to comply with section 8.3.10, and for seismic design category B building, we have to comply with section 8.3.9. So this is very important. Now you know the zone. If you know the site condition, site class, then you can determine the seismic design category. If you choose a certain building system, structural system, you can determine what height is allowed based on the seismic design category. You can determine the value of R, CD, calculate the load, design the structure, and then while detailing, follow these. Only this is the way you can make sure if a structure is seismic design category D, C, or B. Okay, Dr. Ghosh will explain in detail about these detailings in relevant sessions. Load combination, as you can see, the load combination is completely different from the previous version. The overload factors are much smaller than the previous version. So that is another important difference, and this is according to SC 705. SC 705 has been followed here. One important point that I want to make, you see the low overload factor of E is 1. It was 1.75 into 1.7 in the previous version. But in this version, this is simply 1. That is, no overloading is needed because the design basis earthquake, DBE, for which we design a structure, that is kind of ultimate load condition. So we don't need to overload that value. That is important. Okay, sorry. Now, let's talk a little about chapter 3, but there will be separate sessions on geotechnical engineering, 2 sessions actually. One will be offered by Professor Zainal Abidin, who was the team leader of the building code updating project, and another will be offered by Professor Mehdi Ahmed Ansari. He was at the steering committee, as a steering committee member of the building code updating project. Now, I don't know, should I mention these things? Maybe I should skip because I think
I think it depends on how much time you have left for
yes,
part
yes,
7. Yeah.
yes. I think this will be covered by Professor Abedin and Professor Ansari. So I would prefer to skip these slides, but just I want to give the information that how many bores should be boreholes should be done at a specific site. You can get some idea, guidelines from the code, things like that. And minimum dimension of footings, things like that. Classification and identification of soil information regarding these things are there. So what should be the minimum strength of concrete and value of slump, workability for different types of foundations? Minimum thickness of footing, I think you shouldn't stick to these. Actually, you have to calculate the thickness. So that's it. So chapter 3 has a lot of things, and a number of appendices are there which are related to chapter 3. So that will be covered by Professor Abedin and Professor Ansari. Bamboo structures, this is a new addition. This is basically taken from Indian Building Code, but some information related to local species of bamboo are included in this chapter, and those informations were collected from Bangladesh Forest Research Institute, BFRI. So both in the bamboo chapter and timber chapter. So there are informations about local species, and BFRI did a lot of research on local species. So these information are from BFRI. So you can find allowable stresses, information regarding modulus of elasticity, allowable compressive strength, bending stress, these for different types of species. And the species are grouped in different groups. And subsequent calculations depend on what group a particular species belongs to, and other things. Concrete material, this chapter is basically exactly same as compared to the previous version of the code. I will still like to mention about some issues, like this is very commonly asked question, that how many sets of cylinders should we collect for testing? So frequency of testing. So this is given there. At least once, this is from ACA 318, at least one set for once a day. If you're casting in the whole day, you have to take at least one set of cylinders. 60 meter cube of concrete. If you're casting more than 60 meter cube of concrete, you have to take more sets of samples. And if the surface area is more than 250 meters square, then you have to take more sets of samples. For a project, there should be at least 3 sets of cylinders. And 3 cylinders make 1 set. If total volume is less than 20 meter cube, then no test is required. 1 set means in ACI, Once in ASTM, three cylinders make one set, but in ACI, according to ACI, it is 2 cylinders make one set, depending on the size. If it is like 6" by 12", then 2 sets. If it is like 4" by 8", then 3. Okay, so this is very important for those who are supervising construction. And this is another question, quite frequently asked question, that if the test result is less than the design strength, should we demolish the structure? What is the acceptance criteria? For samples which are cured in the lab, you have to understand, you'll collect this cylinder in the field and send the cylinder to the lab. That will be cured in a tub in the laboratory, so completely immersed, so fully cured. So if the samples are cured in the lab, then average of 3 sets if must be greater than the FC prime. But average of 1 set may be less than FC prime, but not less than 3.5 megapascal. So suppose your the design strength is 21 megapascal, say. Now you are getting average of 1 set is 18 megapascal, right? So is that okay or not? That is okay, no problem, because that is within this limit. But average of 3 sets must be greater than FC prime. Okay, this should be clearly understood. But for field cured samples, where you don't send the samples to the lab, you send the samples just before the testing, you cure it at the field. In that case, even the average, probably this is wrong, average of 3 sets can be less, this is wrong, this must be, procedure of curing shall be improved. Okay, no, it's right. Procedure of curing shall be improved. So suppose you are getting average of 3 sets less than 85% of FC prime, or average of 1 set is less than these, then you have to understand that your curing method is faulty. You have to improve the curing method. Now, even after that, if the concrete strength is low enough that the criteria are not met, in that case, what to do? Just demolish the structure? No, still you have other things to do. Like you can cut cores, you can take core samples, and then if the average of 3 cores is greater than 85% of the FC prime, then that's okay. It doesn't have to be greater than FC prime. Just greater than 85% of FC prime is okay. And each core must be greater than 75% of FC prime. Even after that, even the core samples, if the core samples also fail, in that case, don't go for demolish right away. Please, you can do a load test. That is, the recommended of load, this is written in detail in the code, how to do the load test. The recommended amount of load you can apply on the structure and take the readings of deformation, and then you can decide if the structure fails even in the load test, then you have to demolish the structure. So this is one important thing frequently asked, so I mentioned this. Okay. Regarding chapter 6, strength design of reinforced concrete structures. Oh, I forgot to mention, it is not here, that in chapter 5, this was chapter 5, concrete materials, all the things are similar to the previous version except one. In this version, there is mention of shotcrete. different type of concrete application. You shoot, you literally shoot using a pipe, shoot concrete to the surface of, say, wall, and by that way you prepare a concrete wall. So that is called shotcrete. So there is a section on shotcrete in this chapter. That is a new addition. Chapter 6, strength design of reinforced concrete structures. I think this will be covered by Dr. Ghosh. So the topics that are mentioned in this chapter are these. So basically the topics, the titles are similar to the previous version, but the formula and the contents are different. This time it is completely similar to ACI 31808, except the stairs. Stairs are similar to our previous version of the building code. Oh, not completely similar. There's some new additions even in the design of stairs. Some tables have been added. Chapter 7, masonry structures. So masonry structures, more or less similar to the previous version. So these are the classifications of masonry. Depends on the cement sand ratio and the compressive strength. Now, how can we measure the compressive strength of masonry? This is mortar, sorry, grades of mortar. So we can make mortar cube and do compressive testing and measure it. Based on that, we can define mortar grade. And this is important for masonry. To design a masonry structure, we need to know FM, that is compressive strength of masonry unit. So to have that value, to determine that value, we can make units of masonry like this. Multiple bricks are arranged with mortar joints in this type of column. They are called masonry units with 3 or 5 brick units, and then we do compressive testing. This is called prism testing. From that we can calculate FM prime and do the design. Now earthquake resistant design, okay, this is important. Masonry, two types of masonry structures are mentioned in the code. One is unreinforced masonry or URM, another is reinforced masonry or RM. Unreinforced masonry is not allowed. Oh, it's written here. For seismic zones 2, 3, and 4, unreinforced masonry is not allowed. Reinforced masonry, but do you see quite often reinforced masonry that reinforcement, steel reinforcement is used inside bricks? You don't see, right? So RM is basically non-existent in Bangladesh. So, but that is URM, that is the most commonly used method of masonry construction, that is actually forbidden this time for zones 2, 3, and 4. Only in zone 1 that is allowed. For zones 2 and 3, there are requirements for reinforced masonry. For zone 4, this is more stringent. So please check these. If you really want to construct a masonry structure, you have to go for reinforced masonry. This is a new topic that has been added to the masonry chapter in this code, that is called confined masonry. Confined masonry is actually quite popular in Latin American countries and in other earthquake-prone countries like Iran. Actually, in the Iranian building code, that is included in the building code. This is similar to the way we used to construct boundary walls. The brick walls are first made, keeping a void in the location where we want to pour some concrete, and it has got a foundation, And here we provide some reinforcement and we pour concrete. So this is somewhat similar to column, but this is not column. This is called confinement. That's why, since we provide confinement in between these brick walls, this is called confined masonry. So the behavior is completely different from beam column frame in the confined masonry. These vertical members, they provide confinement. They don't actually carry the lateral load. The lateral load is carried by the walls, the brick walls. So that is the basic difference. So all the details regarding this confined masonry is mentioned in this chapter of masonry structures in the building code of part 6. Chapter 8, detailing of reinforcement in concrete structures. I think Dr. Ghosh will cover these, and I have mentioned some sections which you have to follow to design according to SDC C, D, B, C, or D. So these are the topics that are covered in this detailing chapter. So all of them are very, very important. So please go through them if you want to design a structure really appropriately. For earthquake resistant design, as I said, if you want to build a structure according to seismic design category B, please follow section 8.3.9. This is mainly related to column ties and hooks. So for seismic design category C, this is corresponding to IMF, and section 8.3.10 is the section that you have to follow if you want to design according to SDCC. The provisions are mostly related to beams, columns, and flat slabs. So the tie spacing, the stirrup spacing, the tie spacing, etc., etc. So these are mentioned in this section. For seismic design category D, you have to follow sections. You have to follow sections 8.3.3 to 8.3.8. So, sorry, this is the repetition. This is mainly related to spatial moment frame. This is important. No flat slab construction is allowed for SDC D type building. No flat slab is allowed, that is column supported slab. You have to provide beams. For moment frame structures, moment resistant frame type of buildings. For other types of buildings like dual system, things are different. But in general, no flat slab is allowed. FC prime, concrete strength, 28-day concrete strength must be more than 21 megapascal or 3000 psi. The ratio of the ratio of ultimate strength and yield stress of reinforcing bars must be more than 1.25, which is actually ductility class D, according to BDS EN. BDS ISO, ductility class D. Now, there's one more thing that I should mention. In the present version of the code, BNBC 2020, reinforcing bar having strength more than 420 megapascal or 60,000 psi is forbidden for ductility class for seismic design category D. So that is one important restriction. Even if say 500 grade steel, even if it has ductility class D, still you cannot use for seismic design category D. So that is a restriction, very strict restriction imposed by this version of the code. So, and the details, the stay-up spacing, tie spacing, ties within joint, hook, angle of hook, length of hook, and width depth ratio of beams, and width of beam as compared to the width of the column, all these ratios, and there are many other uh, requirements that you have to follow if you want to construct a D type building. So these will be covered in detail by Dr. Ghosh. Let me go forward. Pre-stressed concrete structures. So this is basically similar to the previous code, but it is rearranged. The sections are rearranged in a different way. So I won't go into the detail of these. Steel structures, there will be separate sessions on these. The topics are these, very extensive chapter. This is important. Seismic provisions for structural steel buildings. This is something new. Structural design for fire conditions. This is also new. So design for fatigue. So these topics are completely new topics, and there are many more details that are included in this version of the code. Timber structures, basically similar to the previous one, but locals, some informations are taken from BFRI, Building for Forest Research Institute, Bangladesh Forest Research Institute. So there is some new additions are there. Ferrocement structures is exactly similar to the previous version, but the arrangement is somewhat new of the chapters. So I'm just skipping these. Steel, concrete, composite, structural members. Oh, I don't have time for construction practices, sorry. Steel, concrete, composite, structural members. This is a new chapter. So we are quite used to designing, what do you call it? Composite slabs, right? That is steel, using steel profile and very thin concrete slab. So that is a kind of concrete composite member, but there are other, even the composite columns, composite beams, and the connections. These details are there, even with the seismic provisions for composite structural systems are there. Now, so I used up probably all my time in describing part 6. So I have very little time for part 7. Still, let's see what's there. There are 5 chapters. I mentioned them previously. So most of the chapters are related to safety. Second chapter is related to storage and handling. And fourth chapter is related to demolition work. So the first chapter, construction responsibilities and practices, their information regarding how to plan for a construction. What are the construction controls? How do you manage constructions? Protection of public and workers and environmental protection. These topics are mentioned there. Planning, there are many things. I won't go into the details of that, but let me mention just one point. First aid attendant. Do you know that the code requires that there should be at least one person trained in first aid for every 100 workers? And that person should be trained, not only should be trained, every 5 years he has to attend a refresher course. But we don't have that kind of training available, so we don't have this type of first aid attendant in our workforce, but that is required by the code, etc. And there are other requirements. Anyway, it's construction control, how to prepare site, what are the permits that are required to start construction, what tests and inspections should be conducted. These things are mentioned. Construction management, uh, time management, quality management, and health, safety, environment management, and cost management. So these aspects are mentioned in the code. So a manager, construction manager should understand them. Protection of public and workers. This is very detailed in the code, how to protect public and workers. So like there should be protective fence and railing. And what should be the height of the railing? What should be the if your construction is by just by the side of a road, what should be the height of the fence? Things like that. Many details are there. So if you read this chapter, you'll understand uh, all the details regarding safety in a construction site. So please go through them.
You have until 10:15, Dr. Rakib, not 10. So you have a little time.
I see. Really 10:15 or 9:15?
9:15, I mean. Yeah, I'm sorry.
So I have 15 minutes.
Yeah, 9:15.
Yeah. I have 15 minutes left. I'm going really fast. Okay. I will slow down a little bit. Yeah. Protection of public and workers in that. Let's see how detailed it is. Use of road and footpath. Many of us have a misconception that for construction, we should not, or actually we're not permitted to use road or footpath. We can, but we must first obtain a permission first from relevant authority, that is Raju. If we get the permission, we can use road and footpath, but shall be more than 1.5 meters away from a railway track. A walkway shall be constructed so that people can take a detour. 1 meter clear passage shall be maintained, etc., etc. So we need to have permission, and there are other requirements that we have to meet, things like that. If we use some place which is near to the public use, then we should have red lights blinking, flashing red lights. You might have seen some of them with the metro rail construction or elevated expressway construction. There you can see in places where red lights flash. So that is actually a code requirement. In places where you need to control the public, you need to have watchmen with auditory signals, that is whistles. Safe load, strength test of, so in places like if you have a platform on top of a walkway, then you should conduct a strength test of that platform. Things like that. Environmental protection of public and workers, protection of existing drainage system and utilities. This is very important. While constructing a new structure, if you damage the existing drainage system, then that may cause a really big problem for public, for other people. So you have to protect the existing drainage system. If you have to, if you have to destroy that, then you should put an alternate system in place, and then you remove the existing drainage system. So these things are important. Protect the soil, aquifers, and water channels existing. While construction, you cannot destroy the water source, existing water source, things like that. This is very important. Protection of air quality, which is not followed in our country. You can, every day you can experience that when you go out in the roads. For example, I can mention one project, BRT project, Bus Rapid Transit project. They're causing so much environmental pollution on the Gazipur road. The dust. So the code requires that you have to minimize the dust flow. You have to sprinkle water so that the dust blow is minimized. Sound pollution. You cannot cause sound pollution and cause problem for others for your construction activities. Noisy activities shall not be carried out from 6 p.m. in the evening to 6 a.m. in the morning in the residential areas. Sorry, this is probably in the residential areas. You cannot continue construction activities in the evening and in the very early morning and on holidays. And there is actually a specific amount of noise, the decibel in terms of decibel that is mentioned, up to which you can make sound. Chapter 2 for of this part 7, storage, stacking and handling. This is also very detailed. I don't know how many of you know about this chapter. In this chapter, these topics are there. I want to specifically mention this classification. This is new. It was not there in the previous version. All the materials are classified in 5 classes of materials. Climatically sensitive materials like cement, if you put it in a moist condition, you cannot use it anymore. Durable materials like steel, brick, etc., they are not that sensitive. Materials vulnerable to rough handling like glass, if you handle that roughly, it will break. So that type of material. Inflammable and or fire sensitive materials like paints. I think you know that paints are very, very inflammable. So they have to be stored very carefully. And hazardous materials like the materials that can cause health hazards like acids or explosives. Those hazardous materials is classified in different classes. So how to store the sensitive materials or hazardous materials or inflammable materials, details are there in this chapter. That's quite interesting. Oh, I don't have those details here, but I would like to mention about some. Let's mention about, do you know how to store cement bags? Can you store cement bags in open field? No, you have to store in a room. But do you know that should the room have any windows or not? Can you put cement bags directly on ground or floor, or should there be a wooden platform? And if you put wooden platform, what should be the distance from the floor? How many bags you can stack on top of each other? All these details are there in the code. So for each and every item, details are there how to store those items. For example, steel. Do you know if you have to preserve steel for a long time? For example, you have already purchased steel, but your construction will say start 1 month later or 2 months later. What will you do? Your steel will rust. What to do in that case? I think many of you know about this, that you can sprinkle, cover the steel with grout, with cement water mixture. That will protect your steel from corrosion. So these details are there. Not only that, different sizes of steels, how you can identify, how to put mark for different diameter of steels. Once you stack the steels, it will be very difficult to understand which one is 20 millimeter rod and which one is 22 millimeter rebar. Things like that. So how to put mark for them? Those details are there. Things like that. And for other inflammable and hazardous metals, many more details are there. So that's it. Safety during construction. This is interesting. So again, I'm saying that let's see how detailed the code is. Helmets for workers. What do you think? The helmets for construction site, helmets that are used by workers at a construction site, and then helmets that are worn by motorbikers, are these types of helmets similar? No. And actually, there are specific standards for these helmets. For construction workers, the helmets, they have to follow these standards. BDS 1265, Bangladesh standard. And for motorbikers, there is a different standard. So now you are quite familiar with the term PPE, personal protective equipment, because of COVID-19. You all know about PPE that are used in hospitals and by health workers. But for construction workers, the gloves, the goggles, the safety boots, these are PPEs. So the term PPE is very common in the construction sector. And by PPE, we used to understand these things: helmets, gloves, goggles. So for all the PPEs, there are standards, and at the construction side, these standards should be followed. Site precautions. This is very common in Bangladesh, that often you will find that in high-rise buildings, construction is going on, and one debris may fall, a brick may fall from top on the head of a pedestrian. And this actually happened in Dhaka. And a person died because of falling brick on top of the head of a pedestrian. So there are restrictions in the code. For tall buildings, the construction, you have to put a nylon net all around in the periphery so that nothing falls from the top. Site amenities, this is very important. Hygiene is very important for construction workers. So these have to be carefully considered while planning a construction site. Okay. So, and safety during construction, for all type of construction activities, what precautions should be taken, they are mentioned in these sections, like while excavating foundation, while driving piles, construction of walls, floors, for concrete work, formwork, scaffold, erection, steel member erection operations, electrification. This is very common type of accident that happens in the construction site in Bangladesh. Many construction workers every year die because of electrocution. So the safety precautions that should be taken for electrical wiring is mentioned in detail in the code that should be followed. And other construction hazard and specific requirements for high-rise buildings. So I won't go into the details of these. So for each of those construction activities, many more details are there. So I'll just skip them. Please read them in this chapter, in this part 7. So now demolition work, this is chapter 4. You see, this is nothing new. This is similar to the previous version of the code. What are there? Precautions during demolition. Detailed precautions are mentioned. Blasting operation and use of explosives. It was there in the previous code too. But unfortunately, still we couldn't use this kind of explosive demolition. We don't have this experience, but it is there in the code. Lowering and removal of disposal materials. This is very important. This is the reason why Rang's building collapsed. The debris after breaking walls and columns and shear walls, the debris was kept on the slab. And then they were breaking those shear walls. The shear walls were cut from the bottom and put on the slab, and they were hammering the shear walls and breaking them. And there were a lot of debris on the slab. So the amount of load was much higher than the design load. And because of that, and the Ranks building was a flat slab building, because of that, the flat slab collapsed by punching shear. And you know, once a punching shear happens, that this is called, what do you call it? That the subsequently all other points actually collapse, and the entire floor collapsed on top of another floor. The next floor collapsed because of the load from the upper floor, and so on. The building collapsed. This wouldn't happen if the workers, if the engineers followed these sections, how to remove the debris, etc. Maintenance and management, repairs and retrofitting and strengthening of buildings. The topics that are mentioned in this chapter are building maintenance, access, records, inspections. These are mostly administrative stuff. There's some technical stuff in prevention of cracks, repairs and seismic strengthening of buildings, but don't expect much from this title, although it is written seismic strengthening of buildings, but none of the modern concepts of the seismic strengthening are mentioned in detail in this section. So that's it. Oh, okay. This is just 9:15. I could finish in time, although I skipped many of the slides. So please pardon me for for the haste that I made. I just wanted to acquaint you with the different chapters, contents of the different chapters. That's all. Thank you.
Yeah, thanks, Dr. Akib. No, that was good. That time is short for all the material you have. Uh, we have a lot of questions. You want to take them one at a
Let
time?
me check. Let me check. Yes. Yes. Which one should I first answer? Push answer? Okay. Okay. Then I'll okay. The chat box is on top of the question answer box, so I'll start with the chat box. Please let me know. Sorry, that I wrote that. Sir, if it is possible to publish Bengali version of BNBC 2020, it would be very difficult. I would be very happy if you could do that, but it would be very difficult because the medium of instruction in our engineering curriculum is English. All the textbooks are in English. So we are familiar with the technical terms, only the English terms. So it would be very difficult to translate, to make a Bengali version of the code that the professionals can actually use. That's it, because we don't have the it will be difficult, just difficult. So I told you yesterday that the BNBC is for professionals. Yes, that's the reason why. But one thing, what about Japan, China, and other modern countries? That is very important. Yes, very good question. In Japan, all the standards and all the codes are written in Japanese. In China, everything is written in Chinese because their education, the medium of instruction in their education system is their vernacular language. That is Japanese or Chinese. All the textbooks are in Japanese or in China in Chinese. That's why they could do that, because they have a very good system of translating things. All the textbooks that are published in the United States, within very short time, they are translated in Japanese. That I found in Japan. They, there is a big industry for that, who are entirely busy with translating English books. And on the other side also, in the United States, there is a big industry who are engaged in translating Japanese texts into English. So we need that type of preparation before we can actually um, initiate Bengali medium of technical education. Okay, they publish their own billing code.
Dr. Akib, I would like to add one thing, for it won't take time. In my observation is, if you are conversant with English and doing the engineering in English, you have a worldwide market for yourself. You probably don't have a worldwide, meaning probably not in China or Japan, but a large part of the world opens up to you. If you can do engineering only in Bangla, then your market is Bangladesh and West Bengal. So please keep that in mind. I think in today's world, globally integrated, that is an important consideration.
That is very important point. Even in Europe, they understand the importance of English. So in many European countries, they prefer English. For example, in Netherlands, the medium of instruction in the doctoral level is English. All their dissertations in English in Netherlands. Then this next question is, as per 1021, when the seismic response modification coefficient R is taken as 3 or less, the structure is not required to satisfy the provisions of this section 1020 unless specifically required by the applicable authority. But as per table 6 to 19, response reduction factor, G-type structure D category is not permitted if not specifically detailed, which seems contradictory. Can you explain? I have to check. I cannot answer right way. Dr. Ghosh, do you have any idea about this?
No, I first of all, am not seeing the questions in your chat box. And something this detailed is difficult to absorb and answer directly. So I think your chat box will disappear when you log off. Maybe make sure to make a copy of the questions, and then we can look at them and try to answer them.
Okay, sure.
Looking at the volume of the questions, I don't think we will even be able to answer 10% with the time remaining.
So, Mr. Nazmul Haq, thank you for the question. I cannot answer this right away. I have to check the references that you have mentioned, and hopefully we will get back to you with an answer. Then, in case of building frame system, entire lateral load is resisted by shear wall or bracing system. Frame only take gravity load. However, during analysis in the commercial software, ETAP STAT, lateral force is distributed as per stiffness of different element column shear wall. My question is, how can we exclude column from taking lateral load in building frame system in commercial software? This is a good question. So you have to have two different models of in ETABS or whatever software you use, STAT, you have to have two different models. In one model, you will apply only the vertical load with the frames only. In a different model, you will apply the lateral load. But in that case, please be sure of the connectivity of the shear walls. That is, according to the stiffness of the shear walls, the lateral load have to be distributed among the walls. So you will need two different models. Dr. Ghosh, please, if you can.
Yeah, the basic thing you have to understand is in a building frame system, the earthquake does not know that you have designed it as a building frame system. So lateral loads will be shared by the columns and the shear walls. The building frame system is a design device. In design, we consider only the shear walls are carrying lateral loads and the frames are carrying gravity only. So our analysis has to be according to our assumption, as Dr. Rakib is telling us. The other important thing is deformation compatibility, that the frame must continue to carry gravity loads as it deforms laterally with the seismic force resisting shear walls. So what we do is analyze the shear walls themselves without the frame. We calculate the deflections, we amplify by C sub D. Those displacements have to be imposed on the gravity frame. It is not only carrying gravity, but also these imposed displacements. The analysis under gravity and imposed displacements is not easy. I understand it can be done, but it's not easily done. So we take indirect ways of doing the second analysis. So that's the full answer to your question. It's a design device, so your analysis has to be according to what you have assumed, not what ETABS will do for you. Okay. Hopefully that is clear. I don't know.
Thank
Dr.
you.
Rakib,
Thank you. That is a very important piece of information. Yes, deformation compatibility must be ensured. What is the difference? Story drift and seismic drift. Story drift is the interstory drift, that is the amount of deformation per unit height between two stories. The story drift can be because of wind load, but when we consider story drift because of earthquake load, then we call it seismic drift. I hope I have answered the question. What is the value long period transition period? Long period transition period. What is the value, Dr. Ghosh?
I do not know about Bangladesh. So the long period transition period, just so that you know, the design spectrum that you are used to looking at, it has a flat top part at the beginning that governs the design of short period structures. Then there is a descending branch that varies over 1 over t, varies with 1 over the period of the structure t, and that governs the design of taller buildings. And then if it is a very tall building, you have a third part to the design spectrum that varies with 1 over t squared. Those of you who are in structural dynamics, the flat top is the constant acceleration part of the spectrum. The 1 over t part is the constant velocity part of the spectrum. The 1 over t squared part is the constant displacement part of the spectrum. Now you go from the second part to the third part at a period t sub L that is called the long period transition period. For the United States, the value of that is 4, 8, 12, or 16 seconds, nothing below 4 seconds. I do not know without checking if in Bangladesh you have a value for T sub L. You will get into the third branch only for very tall buildings, 40 stories and higher, or very long span bridges. So most of the time we do not deal with T sub L or the third branch. So I don't even know if you have the third branch in your in the in BNBC. You must
We
have
have, we
seen.
have,
Yeah. Okay.
we
Okay.
have the
So
third branch,
okay.
and this is related to the site class. I think there is a table which
Okay.
for different site class, The values of TL are given
Okay.
in the code. So when to check story drift? Because for seismic load, we have to check seismic drift. For wind load, overall sway should be within H by 500. Yes, for wind load, we have to check the overall sway at the same time. The story drift criteria have to be met also. So for wind load, we have to check both story drift and overall sway. While checking the criteria for story drift, you have to use the combination of different load combinations. But while checking the sway, overall sway, you have to check for only for wind load. That is the difference. Then question 2, is occupancy category 3 only for assembly area or any structure, residential or industrial, which have occupant more than 300 people? Yes, yes. If the number of people residing in a building is more than 300, it will be automatically be occupancy category 3. Dr. Ghosh, am I right?
I again, without looking at the BNBC table, I do not know. These things keep on evolving. So it is better to check the table exactly as printed in the code.
Yes, it is clearly mentioned there.
Yeah, okay, yeah.
What is meant by troughs used as infill wall? What is meant by TRAFS, troughs used as infill wall? I'm not sure.
I am not familiar with TRAS. Sometimes we would model the wall as a truss, but no, TRASS I'm not familiar with. I don't know.
I see. Probably it should be truss. Or
Yeah,
troughs.
I guess that's what it is. Yeah.
Okay. The next question I don't understand. Interstory drift is less or equal to 0.005 H. And no question is there. A structure where 80% are shear wall and 20% are column. In this case, is it mandatory to carry 25% of lateral load by framing? If it carries 25% of lateral load, seismic load, lateral load by framing, then we'll call it dual system, otherwise not. Otherwise, it will be either moment tracing frame system or building frame system.
Can you read the question one more time, Dr. Rakib?
A structure where 80% are shear wall, I don't know how, is it based on stiffness or not, I don't know. A structure where 80% are shear wall and 20% are columns. In this case, is it mandatory to carry 25% of lateral load by framing?
It's yeah, the question is a little confused. If you want to design a shear wall frame building as a dual system, then you will have to do an interactive analysis with the structure that has frames and walls. And when you do the analysis under code prescribed seismic forces, you will see that near the bottom of the building, almost 100% of the shear goes to the shear walls. And as you move up the building, the frames pick up more and more, the shear walls unloading on the frames. So if you design your building just based on the interactive analysis, you will be designing very weak columns at the base of the structure. All the shear, remember, is going to the shear walls. So we have a backup frame requirement. The frames independently of the shear walls must carry at least 25% of the design lateral loads. So this requires a separate analysis to make sure that the frames are in fact the frames are designed to carry at least 25% of the design lateral loads. So this is a consideration only in a dual system. If it is a different structural system, then the 25% criterion is not in the picture.
Next question is, interstory drift is less or equal to 0.005 H. Is it correct to say? Because when we divide deflection by story height, that is called drift. Why delta is not called deflection instead of drift? I'm sorry, it is probably you are right, but the language in the code in BMBC is verbatim to the language of AC7. And in AC7, the language is like this.
I think there is quite a bit of confusion I see. So in seismic design, everything, all the limits apply to interstory drift. In seismic design, we never look at the total sway of the building for control purposes. Interstory drift is the deflection at the top of a story minus the deflection at the bottom of the same story. Interstory drift, this will be in inches or centimeters or whatever. When we divide that by the story height, we sometimes refer to as interstory drift ratio. Okay. So in seismic design, it is interstory drift, sometimes just story drift, same thing. In wind design, in US practice, we do not look at interstory drift. What we try to limit is the total deflection of the building as a percentage or fraction of the story height. Like you have total deflection not to exceed total height over 500. In US codes, there is no limit on wind-induced deflections because the limit requires, so the calculated deflection must be within height over 500. The calculated deflection depends on your stiffness assumption. If you take cracked sections, you will calculate higher deflections. If you take gross sections, you will calculate lower deflections. If we cannot regulate the stiffness assumptions, if we cannot tell you precisely how you will calculate deflections, the limit is kind of meaningless. So this is why we have in US codes never imposed a limit on wind-induced displacements. There are design office practices. Height over 500 used to be back in the old days. Now it is relaxed to height over 750, height over 800, something like that. But it is not a code requirement. And again, in seismic design, it is interstory drift. In wind design, we look at the total deflection of the building as a function of the height.
So should we continue with other questions, or since it's already 9:35?
After 9:30, yeah. We probably cannot. I personally have another meeting starting, but apart from that, judging by what I saw in the Q&A box, it will take a couple of hours probably. So we will have to. This is the first week. We'll have to figure out a way of. I think what we are doing is what we'll continue to do. Take as many as we can and then try to answer the rest afterwards and post them on our website.
So I have taken a copy of the questions.
Yeah, good.
From the chat box and also from the
Q&A
box.
Yeah.
So all the questions are only to me. Oh, but it's
the chat box questions are to you. My chat box has other questions, but the Q&A box is common to both of us.
I see. I'm finding it difficult to copy the Q&A questions.
We'll make a copy, so don't worry about the
I,
Q&A. Yeah,
okay, I've
yeah,
I've taken a copy of the chat box.
yeah, yeah. That's the one we don't have access to.
Okay, okay. So
Okay, I
thank you
think
so much.
yeah, I think we will conclude. Thank you very much, Dr. Akib. Uh, Two people on our staff, Prodas Gupta and Maria Iglipe, uh, conducted the seminar and took care of a lot of stuff behind the scenes. I definitely thank the two of them. And most of all, I thank everybody who attended. I was looking at the participants' numbers. We got to 435 at the peak. 435 people actually attending. So please keep on doing that. We have two seminars next week. Both of them will be by Dr. Rakib, and then the following week I will do two seminars every time, Tuesday and Wednesday, and that time will be the same as today, 7 to 9:30 Dhaka time. Okay. So have a good rest of the week. We will see you next week, and thank you again very much for attending and making this seminars a success. I regret that we don't have a better way of answering questions, but the attendance is large, the volume of questions is large, so it's just not practical to try to have everything answered on the spot. Thanks again.